Okay, so I want to talk about the Mars helicopter. So we just had a NASA launch of the Mars rover Perseverance, and it's going to carry this helicopter to Mars. It's going to fly around, and I think that's super awesome. So I want to model this helicopter in terms of really find out what kind of power it would need to fly. And as long as I'm doing that, I might as well look at things like the human-powered helicopter, which is real, and other helicopters. So let's start with the basic model of a helicopter. If this was a cowl problem, this would be a spherical cowl. Instead, I just have a plain, generic helicopter. There is a gravitational force pulling down on the helicopter. But if it wants to hover, there has to be something pushing up, and that is some type of air force pushing up on the helicopter. If I look at the forces in just the y direction, then these forces have to add up to zero if it's hovering. So F air minus mg is equal to zero. That's a scalar equation, not a vector equation. And so that the air has to be equal, the F air has to be equal to mg. Just a quick comment about the tail rotor. Normal helicopters have a tail rotor because they have one large main rotor that spins. It exerts a torque on the body of the helicopter, and the tail rotor is pushing perpendicular to counteract that torque. The Mars helicopter has two main rotors that rotate in opposite directions so that the net torque is zero. I just think that's kind of cool, but that's why it doesn't have a tail rotor. It is a helicopter, though. Okay, so here we can start with our very fundamental basic model of how a helicopter could hover. Let's say that it takes air above it and the cylinder of air that's the same diameter as the rotor and throws that air down. And so it takes that air and increases its velocity. So this air has a height, it's a cylinder with a height h and a diameter of something with a surface area of a. Now, since the air is going to increase in velocity, there has to be a force on it, and that force comes from the helicopter. But forces come in pairs. So if the helicopter pushes on the air pushes back on the helicopter with equal and opposite direction. So the helicopter is pushing down on the air, and that pushes up on the helicopter. So that's how the helicopter can get a thrust force, and that's that F air pushing up right there. So I can want to calculate the magnitude of the air force on the helicopter by looking at the change in momentum of the air below it, that cylinder of air. And so the momentum of the air would be the mass of the air times the velocity of the air. I don't know, it's just going down with some velocity. We can find out what that is later. To find the mass of the air, it's just a giant cylinder of air. If I know the density of air, which I do, 1.2 kilograms per cubic meter, and the volume of that cylinder, area times height, then there you go. So then the momentum of the change in momentum, the air force depends on the change in momentum. That's just from the momentum principle. But the initial momentum was zero. I'm going to say it started at zero. There's air above the helicopter. It starts at rest. It gets thrown down with some new velocity. Now, what about that time interval? Well, I can start with the definition of average velocity. This just says take the velocity before the air was moving and the velocity afterwards, which is v. I don't know what that is, but it's v. And then divide by 2, I get the average. And then I can take the length of the cylinder of air. That's how far it went. I can say average velocity is change in the position divided by change in time, but the change in position is h. That's how far it moved. I don't know delta t, but I can solve for it. So delta t, the time it took, would be twice the height divided by the velocity. And that's because it's not going at a velocity v the whole time, which I don't know. I'm just making stuff up. Okay, I'm making up stuff. That's what we do. Okay, so now if I use that time interval in my F air equation, I get the change in momentum over the change in time. So I get rho a h v squared divided by 2h, and the h's cancel, and there you go. If it's hovering, then this has to be true. The rho, the density of air, times the area of the rotors times the velocity of the air squared divided by 2 would have to be equal to the mass of the helicopter times g, the gravitational field. That's to hover. Now, what about the power to hover? So here I can start with this velocity, this air above the helicopter that's not moving, and then down below it is moving with some new velocity. So it starts with the velocity 0, and then it goes to velocity v2, and I can define the power that the helicopter needs to move that air, to increase the speed of that air as the change in energy over the change in time, where in this case the only energy I want to worry about is the kinetic energy of the air, where kinetic energy is 1/2 mv squared. Now, you could say, well, there's other types of energy. There's change in gravitational potential energy. But I wasn't calculating a gravitational force on the air anyway, so it's all cool. This is just an approximation. It's mostly just a change in kinetic energy of the air. So if I put in that value for the kinetic energy, and I use my time interval from before, then I get a power of mv cubed over 4h. I'm missing something here. Where's the other v? Oh, and then that's right. So then I put in my expression for the mass as rho a h, and I get the h's cancel again, which is good. The power shouldn't depend on how big of a piece of air I pick, because it's continuously moving down. And then so I have these two things together. So I have this is the same expression for hovering for the velocity of air, and then I have the power of the air depends on the velocity cubed. You could combine these into one equation, but it looks really weird because it's got the raised to the 2/3 power, and I don't really care. So you calculate the velocity based on the mass of the helicopter and the size of the rotors, and then you plug that into the power equation, and you get the power. But this shows something, because there's two ways I can make a helicopter hover. I could have a small rotor, but I'd have to throw down the air very fast. Or I could have a large rotor, and I'd have a lower airspeed. But you see in the power, you have that velocity cubed, right? So the key is to have, if you want a lower power, you want bigger rotors. And here is an example of that. This is the Gamera 2 human-powered helicopter from the University of Maryland. It was an entry into the Sikorsky Challenge, the Sikorsky Prize, which was to make a human-powered helicopter. It had to fly in like 3 minutes, 10 feet high or something like that. So, and this is their thing. But you'll notice how huge it is. It has 4 rotors, and they're giant. So you can use that. You could use that to calculate the velocity with the rotor size and the mass of the helicopter, calculate the velocity of the air, which I'm going to do later, and then use that to put in the power, and you could calculate the power of the helicopter. And this is really why I started with this whole calculation. I wanted to calculate how hard that would be. Okay, here's where you should say, you can't do that, right?
No, he doesn't just come to a meeting and say bugs.
Ants and stuff.
So that's from Big with Tom Hanks. He is a kid, and he comes into this. Why am I even telling you this? Well, I'm going to tell you anyway. So he comes into this boardroom. He works for this toy company, and he has these ideas about toys. And then the adults, who he looks like an adult, are like, you don't just come in and say bugs. He was talking about this robot that could turn into a bug or something like that. And the same thing's true here. You say, well, you can't just be a physicist and use these basic models of physics and expect things to work. That's just not how life works. Helicopters are complicated. You're not a helicopterologist, I guess I'd be an aeronautical engineer. You're a physicist. You're just using basic fundamental physics. It doesn't work in this situation. And I completely agree with you. It shouldn't work. On campus, and I made the video, and I've been waiting to use this video forever, right? Because you see something like this, you go, I can get a video, and I'm going to use it for my blog post or something, and here it is. So there's a real helicopter taking off, and it really flies, and it really has an engine. And so if you go to Wikipedia, you can look up everything that you would ever want to look at. You can find a helicopter, you can find a Black Hawk, and you can look up the mass of the helicopter. You can look up the size of the rotors, and you can look up the engine power here. Do I have the what's that called? The Black Hawk? Is that AW1? I don't know. It doesn't really matter. I had a whole bunch of stuff. And then the Chinook has 2 rotors, right? So you can look up all these things, and then I can use that to test my model, because I have the power listed, and I can calculate the power. And here's what I get. I'm gonna let you just chew on that for a little bit. So this is the listed power on the horizontal axis versus the calculated power using my bogus model. And the slope of this line is not 1, okay? But that's okay. But the line is linear. So there could be another efficiency factor in there, and there should be, but still, it is not completely crazy. And I was really surprised that this worked even at all, but it did. Okay, so you can use that basic idea to get a rough estimate of the power for a helicopter. What if I do the same thing to look at the speed of the air coming out of the rotors? So I could take the area and the mass of the helicopter and use that to calculate the velocity of the air, and I get this. The velocity is a function of mass. I don't know, it's big mass. and you see that there is no real relationship here. But we do have this range of speeds. I have a speed for really small helicopters of around 17 meters per second up to 30 meters per second, but then it goes back down. So there's no real relationship between these, except that air for some reason has to go between 16 and 30 meters per second. I have no idea why, but I already said I'm not a helicopterologist, so it's cool. Okay, let's go back to the human-powered helicopter, the Gamera 2. I can estimate the mass. I can get the rotor size and calculate the area. And from that, I get a air thrust speed of 1.68 meters per second. So you can see, compared to those helicopters, how much slower this thing is. And with that, I get a power of 755 watts, which is crazy high, but possible. This is from the Bicycling Science book, David Wilson, really fun book. And so he has this awesome graph in there. You can find other ones on there similar to this, but I like this one the best, that for humans. So humans can exert extreme levels of power for a short amount of time, but for a sustained level of power, then you really drop down. So here this graph goes up to 300 watts or something like that, but the time, the vertical scales in hours. So could you do this for 3 minutes? I think you can do probably 755 watts for 3 minutes, but I mean, I can't. Okay, I'm in that average human range, or maybe healthy. I might be a healthy human, so I could do like 225 watts for 10 minutes or something like that. So okay, so that is a real video, the human-powered helicopter. What about the Mars helicopter? So there's a couple things that are really weird about Mars that would make it different from flying on the Earth. Number one is the gravitational field is less. So Mars is smaller and lower mass, but importantly lower mass than the Earth. And so the gravitational field on the surface of the Earth is 38% that of on Earth, where we have a 9.8 newtons per kilogram. So that means it's easier to get up because the gravitational force pulling down is less. But the density of air is also less. It's like 1% the density. So that's bad, because if I have a higher density air, then I get more thrust when I push that air down. So you have these two competing factors. So the mass of the rover, the helicopter, I'm not sure. This is the one I used in my original calculations. I used 1 kilogram, and I looked this up a while ago, and it might have changed. And NASA lists the power as 220 watts. But, I did my own calculations using my model, and I got the power of 373 watts. Again, so I didn't include that efficiency in there. And I get, so the thrust speed of 200 meters per second. That is important. Look, think about that. It's a different aerodynamic situation on Mars with lower density. It seems likely that you could get it down there. I was looking at some other things. I'm not going to go into my calculations or at that Trinket Python script. I did this in Python, but what the idea is to fly it for 23 minutes and use solar panels to recharge it, which is hard on Mars because you don't have as much sunlight either. But could you do that? How much could you do that? So it's a great homework problem. Compare the battery listed power, the battery energy listed by NASA compared to an iPhone battery. It's about like an iPhone. That's kind of weird, but that's true. iPhones actually have a lot of energy stored in them. But okay, so that's the Mars helicopter. But what about something that's not real? This is not real. This is the Shield helicarrier from the movie Avengers, and it starts off looking like an aircraft carrier, then like, hey, no, wait, we can fly. So it's a flying aircraft carrier. Okay, so let's make some assumptions here. Let's say it's like a Nimitz-class aircraft carrier. It floats like one, and it looks about the same size. So I'm just going to say it is. And I can use that to find out how long this is and how big the rotors are. So I get a rotor radius of 17.8 meters. And using the mass of a Nimitz-class aircraft carrier, I can also calculate the thrust speed of the air, and I get 642 meters per second. Boom. That's weird, right? Because remember, real helicopters, they were around 30 meters per second. Mars doesn't count because that's on a different planet with different atmosphere. And so with that thrust speed, I can then calculate the power, and I get 3 times 10 to the 11th watts. A real Nimitz aircraft carrier has a nuclear power plant of 2 times 10 to the 9th watts. So you'd have to have a lot more power. But that doesn't mean it's impossible. It's Avengers, right? So they could have some other power source. They could use the, all that stuff Nick Fury had I can't remember which one of the technologies from the Red Skull that they were working on that they stole. Okay, so but let's do this. Let's fix the helicarrier, and I decide to fix the helicarrier. So here is the helicarrier. If I use a thrust speed of 50 meters per second, I think that feels a little bit more realistic compared to the other ones. But in order to do that, you're going to have to increase the size of the rotors. So I did. So there's my new rotors. I drew that picture. That's what it looked like. Haha, it's funny, right? But I just want to point out that I wrote about this some point in the past, and I said, oh, come on, the helicarrier. And I love Avengers. Huge Avengers fan, and I don't care if it's not real because that's what makes it fun. But I wrote a blog post about that, and then the next time you saw a helicarrier was here. This is from Captain America Winter Soldier, and you see they've read my blog post and they fix it. See, they have like thrusters coming out the bottom, and they say, oh, the air is going a lot faster. I'm just making that up. I don't know if that's true, but that's true. Someone from Marvel Cinematic Universe should contact me and say, yes, we're going to give you credit for fixing the helicarrier, and we apologize for not putting your names in the credits, but that's cool. So that's it. Physics. You can pretty much model anything. It might be wrong, but it might not be. And if you can use it to predict things that you couldn't actually measure, like a shield helicarrier, then you're all good. And that's it.